So our second lesson on AP thermodynamics, wrapping up the enthalpy theme. Okay. We're going to look at internal energy under two particular constants, constant volume first. So change in internal energy of the system, I'm not going to write the system subscript, is Q plus W. We're going to look at constant volume, so I want to break that work term down into PV work. So instead of plus minus PV, I'm just going minus P delta V. And then we're going to simplify this a little bit more. If we're under constant volume, so we're in a rigid container, volume can't change. Volume is now a constant. So delta V is now 0 under these conditions. So this whole term is also 0. So under constant volume, internal energy is just heat, Q. And this can sometimes be written as Q sub V for constant volume. We're going to look at internal energy at constant pressure now. I'm going to start at the same point. Internal energy is work, or heat times work. Do that same substitution for work. So I'm going to stick in the Q sub P right away. So change internal energy is Q at constant pressure minus P delta V. Can I drop anything? And I can't. We're going to have a change in volume. Our pressure is constant. We can't drop any terms here. We can't further simplify. Okay? But I am going to rearrange this and solve for Q at constant pressure. Okay? So this is a rearrangement now. Again, not a simplification. So when I get Q at constant pressure by itself, I'd be moving this to the other side. So the minus becomes a positive. Okay. Or I'd have to go negative work. And this is our definition, our advanced placement definition of change in enthalpy. Change in heat, or Q at constant pressure, is enthalpy change, which would be internal energy taking away the work from the internal energy. So there's a slight difference between internal energy and okay. So let's compare. We're going to compare internal energy versus enthalpy change. Work is our difference. We're going to be back to doing some work calculations. So change in internal energy is Q plus W. If we do this under constant pressure, that Q is our enthalpy change. So this is kind of a new substitution. And then we've got a couple options. I could go that way to calculate my work, and I just want to summarize the two ways that you can get work in an experiment. Okay, we've got minus P delta V. Okay? You could solve for the change in volume. That might be the harder way. You might have to do some stoic and know the change in volume. So you might have to figure out how many moles of gas you made and then turn that into a volume. What's often simpler, okay, is the minus nRT version. Okay? If you just know the change in moles, but you have to realize this is the moles of a gas that's going to change the volume. So it's not the change in moles of everything, it's just the change in moles that does the work, just the gas. Okay. And R is 8.31. In Chem 30, it was 314. Your AP formula sheet is 8.31 joules per mole per liter. Okay, and that's given to you. Okay. Or you can just divide that by 1,000 and express it in the kilojoule form. Okay, so again, that's not a memorize. It's on your AP formula sheet. Okay. So we're going to compare enthalpy. We're going to compare enthalpy and internal energy. How big a difference is it? Is it a 50-50? You know, they have similar values. So this is the example we're going to kind of build the comparison from. Calcium metal can react with water, making calcium hydroxide. It is not very soluble. We'll just switch that to solid and you get hydrogen gas. There's only one gas produced. So this question's easier to do the change in volume because there'd be no volume of gas at the beginning and we just got to focus on the hydrogen at the end. Okay. And the enthalpy change we're given, minus 430 kilojoules. Okay. Now in AP, they express this a little bit different. We go minus 430 kilojoules in Chem 30. AP would go kilojoules per mole of reactant. Okay, it makes it look like it's a molar number, but it's not. Just AP goes and expresses everything per mole. Okay, it's not per gram. Okay, it's per mole of chemical. Okay. So I'm going to kind of go through and give you one example of using both the PV work and the nRT work. So it's going to be a bit redundant, but again, this is meant to serve as an example. So we need, this is really just a logic statement based off the equation. Okay. At standard conditions, 1 mole of calcium, well, that's coming from that one stoichiometric coefficient, okay, will produce 1 mole of hydrogen gas. And we also know that 1 mole of calcium is going to have that minus 430 kilojoules as the enthalpy change. So again, this isn't really a given circumstance. This is just a logic statement using 1 mole of calcium. And I want to determine internal energy, and we can compare it to the enthalpy change and kind of answer the question, what is the difference? How do they compare? So I'm going to go up and pull kind of from here. Internal energy is enthalpy change plus work. Again, we got these 2 different ways we could solve for work. I'll do both. You would never do both on a test. Okay, I've got the minus P delta V, and I've got the minus nRT. Okay, this will be the easier way. I'll start with the harder way first. Change in internal energy. What's the enthalpy change? Minus 430 kilojoules. I'm going to keep writing it the Chem 30 way. I'm not going to go per mole, but when you look through examples in AP textbooks, you're going to see that per mole of reactant. Okay. And then what's our PV work? We need to know the pressure and the change in volume. Well, standard conditions are pretty much an atmosphere. We need to know the change in volume. We're going to have to do some Chem 20 gas calculations that you might be a little rusty with. What is the final volume of gas? Well, there's no gas there, there's no gas there, there's no gas there. That's the only thing we need to focus on. What volume of hydrogen would be made at the end? Okay. Well, we know there's going to be 1 mole of hydrogen from our stoichiometry. Okay. 1 mole of calcium creates 1 mole of hydrogen. So we need to know what's the size of 1 mole of hydrogen at SATP. So in Chem 20, you could use PV equals nRT. That would work. But we have molar volume at SATP and STP. There's a constant ratio to volume per moles at these two conditions. At SATP, there's 24.8 liters per mole. Equals our volume, and we want to know our volume for 1 mole. Again, if you forgot this, you're doing an exam, you could always go back to PV equals nRT and solve for your volume. Okay? Your pressure is an atmosphere, 1 mole, look up R, and temperature would be 298 under standard conditions. This is a shortcut that you learned in Chem 20. So the volume is 24.8 liters. If I cross multiply and multiply by 1, it's 24.8 liters per mole times 1. So I'm skipping rearranging that. So the final volume is 24.8 liters. The initial volume of hydrogen is 0. There's no gas at the beginning. So I just need a little room to finish this because we got some unit conversions to worry about. That would give us liter atmosphere units. I haven't closed my bracket yet. What units would we get within that unclosed bracket? And that's why I haven't closed it. We're going to get joules, but we've got kilojoules there. So I've left it open just to convert to kilojoules. I want to get rid of my joules. You could obviously get your answer and then just use a formula to convert it if you wanted to. 1 kilojoule is 1,000 joules. Okay. I didn't bother converting my joules in the lesson 1 example because I didn't have to, but here we want to compare kilojoule units. So atmospheres, liters, joules. So our change in internal energy. I want to leave this as 2 pieces so we can do our comparison. Is minus 430. Our second piece comes out to 2.5 kilojoules. I've got too many sig figs, I know that, but just for the sake of comparison, I'm not going to round it yet. To 433 is probably what I'd round this to. Okay? But this isn't a mathematical question, really. It's articulate a comparison. And is there a big difference between the two? Okay. Internal energy is really 433. Enthalpy change is 430. There's not a big difference between internal energy and enthalpy. Okay. Most of the energy is coming from Q. That was the only thing we measured in Chem 30. We never measured the work, and it's not going to be typically a large amount of energy, and it could be zero. Okay, there's lots of reactions where there's no work done because there's no volume change. Okay. I'll just quickly lay out what is probably the easier way. Okay, you could get the work from minus change in nRT, and you want to see this is way faster. So again, this is redundant. Okay, I want to spend most of my time on the trickier option. Change in moles. Hydrogen moles at the end, or gas is 1, hydrogen at the beginning is 0. So the change in moles is 1, or exactly 1 in our stoichiometry. Okay, times R, 8.31 joules per mole per liter, times our temperature. Per mole per Kelvin, and times 298 or 298.15, and you get to 2 sig figs, the same I just jumped ahead of my conversion, so I'm just slowing down. Minus 2,500 joules, or the same kilojoules. You should get the exact same. Okay, so do whatever method is easier. A question might be setting you up to either do the minus P delta V or the nRT. If you're starting from a stoichiometric equation, the nRT is probably the simpler way. Okay. So that ends internal energy and enthalpy change. So we're just going to talk about enthalpy. Okay. So, okay. We've previously learned how to predict enthalpy changes using kind of Hess's law, using formation values. Okay. We're going to learn another way to learn to predict enthalpy changes. Okay. Enthalpy change is really the difference in potential energy. If we know the energy stored in all the bonds, or we know the difference in energy in all the bonds, we can predict the enthalpy change. Okay. And that's what we're going to do. Now we're going to need to be able to balance equations, and we need some organic chemistry to know what bonds actually broke. Single bonds, double bonds, triple bonds. So we're going to burn methane in this example. Methane plus oxygen gas. It's going to make carbon dioxide gas and water. I'm doing complete combustion, not incomplete. When this is balanced, I'll stick in the ones for emphasis. We need 1 methane, 2 oxygen molecules, and 1 carbon dioxide and 2 water vapors. Okay. We can predict the change in potential energy, okay, the enthalpy change, okay, by knowing the difference in energies in the bonds at the beginning and the bonds at the end. I said this a lot in Chem 30, but we never did the math, okay? But now we have the values to actually do the math, see what bonds changed, see what that energy difference is. So we're going to sum up the number of moles, but we're not using formation values, of the bonds that were broken. Okay. Bonds broken require energy in, and that would be positive values. Okay. So that's why there's no sign in front, okay? I'm going to raise this, but you know, this is our endothermic piece, okay? What's the positive, okay? We're going to subtract. We're going to look at the bonds formed, which are exothermic, hence the minus. We're going to sum up the moles times the bonds formed. Okay? So this is really no correlation to moles times change in enthalpy of formation. Okay? We're doing the bonds broken, the positive piece first and the negative piece second. Okay, so we're going to make a bit of a list. Let's make sure we understand our chemistry first. So we have methane. This one's pretty simple. Carbon has 4 bonds. There's 4 H's, so there's 4 carbon-hydrogen bonds that must be broken because we have no carbon-hydrogen bonds at the end. So that's one thing that'll go on our list. We have diatomic oxygen. Okay. We have to use some Chem 20 Vesper to think of how many bonds are there between those oxygen atoms. 1, 2, 3. Okay. So you have to remember electron dot diagrams. Okay. Oxygen atoms have 2 singles. So oxygen, an oxygen molecule has a double bond. Okay. They both need to be broken. There's no O-O combinations. Carbon dioxide, carbon has 4 bonds, 2 to each O. Okay. Both of those are formed. There's a CO formed on that side and a CO formed on this side. And last, we've got our water. I'm not going to bother explaining the structure of water. If there's anything you should know well, it'd be water. Now, there's 2 of those waters, and each water has 2 new OH bonds. So we got to sum a fair number of pieces up. Just going to summarize all those bonds, and then we'll do the math and be done. So our 1-methane, there are 4 CH bonds that need to be broken. Okay. For our oxygen, there's 1 oxygen to oxygen double bond. When you're looking stuff up, there'll be oxygen-oxygen single and oxygen-oxygen double. We got to grab breaking both the double. On our product side, so red is what we're breaking, blue is what we're forming, so there's 2 carbon-oxygen double bonds. And last, we get to water. We've got 2 OH bonds in each water, but then there's 2 molecules, so 4 of those in total. Okay. Now I've got one thing I need to fix. Okay. In going through, I was doing everything for 1, and where do I need to update that I didn't factor in my stoichiometry somewhere? The oxygen. Okay. So just going a little quick, there's 1 oxygen-oxygen double bond, but there's 2 oxygens. So in going a little quick, I didn't double that. Okay. Now we've got our list of what we have broken on the left and what we have formed on the right. So now it's just math and looking things up and not making sign errors. So our change in enthalpy, we're going to do the bonds broken. So there are 4 moles, and I'm going to look up CH. This is 413 kilojoules per mole. Everything is going to be positive. We're looking up bond energies, energies to form those bonds. Okay. Now we're on to our oxygen. There's 2 moles of those, or 2 of those, times 498 kilojoules per mole. that's it for my bond breaking. So that's all my positives. Now I can get into my negatives, my bonds formed. 2 moles. Now CO2 on your sheet is in a special CO category. So make sure you look up not the regular CO double bond, but the CO2 one. So your sheet says 474, I've got a copy. C to oxygen is 745 kilojoules per mole, unless it's a little abnormally high if it's in carbon dioxide. It's almost 800 for all of those CO double bonds. So I'm using the almost 800 number. And last, we have the water. There are 4 OH bonds between the 2 waters. And like I would have done in calculating enthalpy in Chem 30, I'd throw this all in and do it in one big line on a graphing calculator, and I get minus 818 kilojoules. Okay, I get a negative answer. That's a good sign. And again, this is another method for predicting enthalpy change instead of formation values using bond energies. Okay. The 2 predictions are typically within 1% or 2 of each other. They both do a pretty good job in predicting enthalpy change. Okay. The one thing I will point out, the most common mistake made is being a little uncareful with carbon-carbon bond when carbon-carbon bonds are broken. So if you have a carbon-carbon triple bond, I'm going to review some 20 AP. This first bond is a sigma bond. And that first bond, I'm looking for it on our table. Okay. Okay. That's the highest energy. The second and the third are lower energy pi bonds. Okay. So if you have a triple bond and you break one of those bonds, okay, maybe this reacts, okay, I'm not going to do a full reaction, but there's some addition and you go from a triple down to a double, you can't just subtract a carbon-carbon single bond off that. You're not subtracting the right bond, okay? The best way to be careful, it's not the only way, would be just to subtract, or sorry, it'd be positive, factor in breaking the triple, and then adding back the double is the best way to take care of this, okay? To go from 3 down to 2. Do not subtract a carbon-carbon single bond to get from the 3 to the 2. You're factoring in the wrong bond. You're factoring in getting rid of the sigma, not getting rid of the pi. Okay? Same thing is true with oxygen. If you go from a triple and an oxygen down to a single, don't just subtract away a single. Take away the 2 and then put the single back. Okay. Last slide to wrap up enthalpy before we get into entropy is just looking at bomb calorimetry. So not very much new here beyond Chem 30. What we already did was specific heat capacity. Okay. Q is MC delta T. That started back in Science 10. You didn't use it in Chem 20, and then we pulled it back in Chem 30. That's our potential energy change. Okay. This is the surrounding energy. Okay. We can equate that to the system. Okay. Now, some sources for specific heat capacity will use letter S, some university texts. The same thing, little s, little c, same meaning. What I really want to talk about is the slight change with bomb calorimetry when you have just heat capacity. The word specific is gone now. Here, Q equals not the mass and the little c. There's a value for the mass and the specific heat capacity all combined together. Okay? There's a reason for this. Maybe the surroundings is multiple materials, multiple metals, some metal and some water. Okay? And this C value takes into account the whole surroundings. Okay? And you still need your delta T, of course. Okay? Okay. So the switch, and you'll have some questions to work on this, MC just turned into big C. So if you know the mass of the material and you know little c, that is equivalent to this big C. Okay. Okay. So joules per gram per degree Celsius for mass would be our grams. So in big C, it's just joules per degree Celsius are the units. There's no mass factored in, or it's been pre-factored in. Okay? And you could flip between one and the other. So in a university or academic setting, okay, and you want to burn food to figure out how much energy is released, you wouldn't do it in open combustion in the lab, you do it in a closed system in a bomb calorimeter. The bomb is inside the blue section, so this would be a very thick-walled, sealed metal container, probably with threads that you can close up the top. The threads will hold it together. It's sealed. Inside is a little chamber that you can put your food, and it's electrically connected outside the bomb, so they can spark whatever is inside. You literally blow up whatever food product or whatever you want to figure out the enthalpy change inside this whole bomb setup, and between the very controlled water and the mass of your bomb calorimeter, there will be a big C value for this device. Okay? And every bomb calorimeter would have a different C value. Okay? The manufacturer might have figured it out, or a technician, or you might have to figure out the C value before you use it. Okay? And the math is really, if anything, it's easier than what you did in Chem 30. Okay? You would figure out the delta T of the water, but the heat for the metal and the water, the whole setup is where all the heat went, the delta T for the whole setup. So you should be able to solve a bomb calorimetry question with a slight alteration to your previous skills. Okay. So bomb calorimetry is the last sort of part wrapping up. Next lesson starts entropy. We're going to look at chaos or disorder. Disorder is a better term to think of in chemical reactions. Okay. What circumstances lead to more or less disorder? And we'll dive into the true answer of what the second law of thermodynamics is, which connects to disorder of the universe. Okay. So in this section, a few questions from AP workbook, AP Advantage workbook 1, or there's a couple questions with little MC delta T versus, or little MC versus big C from a previous book, so I've just inserted those into the slides. You don't have to look those up. Okay.